Welcome back to the workshop. This is going to be a continuation of Module 5 on rigid pavement design. We've already discussed and presented the distress and/or performance indicators of jointed plain concrete pavements. Module 5.1.4 focuses on details related to designing jointed plain concrete pavements and, more importantly, adjusting the design to satisfy the design criteria. There are 5 learning outcomes of Module 5.1.4 on Jpcp designs. These outcomes include define and locate the Jpcp design features that are included in the software, identify the types of pavement materials permissible in a Jpcp design strategy, illustrate the impact of key design features and input variables on the predicted Jpcp distresses, explain the assumptions used in the Jpcp design strategy, and finally, list the Jpcp design features to adjust or change the design to achieve an acceptable design. Before getting into the details of the rigid pavement design strategies and adjusting the design to satisfy the design criteria and reliability levels selected, there are 2 chapters in the Manual of Practice, chapters 11 and 13, that include information and suggestions for rigid pavement design. We already reviewed chapters 3 and 5 at the start of Module 5.1, so this module will simply focus on chapters 11 and 13, which include sections 11.2.2 on new Jpcp design strategies, and Chapter 13, Section 13.5 on interpretation and analysis of the trial design for rigid pavements. Now we'll go ahead and open the MEPDG Manual of Practice and briefly go through these different sections in chapters 11 and 13 in terms of what will be covered within this module on Jpcp pavement design. So we'll first of all go down to chapter 11. Pavement design strategies, specifically the section on new rigid pavement design strategies in developing the initial trial design, and specifically for Jpcp designs. So this section provides a brief overview of the recommendations for different key Jpcp design inputs and design features that we'll cover in this section. So I'm not going to list them specifically, but the user or designer is encouraged to review these as we go forward. The other item is on Chapter 13. Chapter 13 on interpretation and analysis of the trial design features. We're going to specifically go to section 13.5 on page 225. Specifically the table 13-4 for providing guidance for modifying or adjusting a Jpcp design to satisfy the performance criteria. And this section simply overviews what the user can do in altering one of the distresses or IRI to meet the design criteria. So table 13.4 is applicable to this section. So with that, we're going to go back and continue now with the presentation. So we're going to start with the structural and site features that impact the performance of jointed plane concrete pavements. This is a screenshot showing the folder and tabs for the Jpcp design features and factors needed for designing a Jpcp. The software will be used to show where the Jpcp design features and variables are located. So we're going to open the software now and go through the factors, the features and factors specific to a jointed plane concrete pavement design. So we're starting with the designs, jointed plane concrete pavement, and we're going to go down to the design properties, and this includes design properties and features specific to a jointed plane concrete pavement. So many of these, or some of these, were discussed in the inputs module 4.4.4 for Portland cement concrete material properties that are inputs to the software. These are more of the design features, and we'll go through these very briefly and then come back to them and discuss them in more detail as part of the presentation. So the first item is dowel joints, the spacing, and the dowel diameter. The user can simply uncheck, and then the transverse joints would not have any dowels. Using dowels, the dowel diameter and dowel spacing need to be defined by the user. A dowel spacing of 12 inches is typically the default value used for most designs. The next is on the erodibility index. This has to do with the base layer or the layer supporting the Portland cement concrete slab, on whether it is extremely erosion resistant to very erodible. And this was also discussed in Module 4.4.4 in terms of which of these should be used. These are tied to the type of material. Very erodible would be more like fine-grained subgrade soils. Extremely erosion resistant would be like where we have an dense graded asphalt concrete base layer. So the next is the PCC base contact friction. Full friction with friction loss at 240 months. So the user can define whether this is an unbonded Jpcp or a fully bonded Jpcp. The months until friction loss defines the time frame in months at which full friction is assumed to occur. Default value is typically 240 months or throughout the design life for some types of materials. But the user has the option to identify or note the months until you have friction loss. The next item is the PCC base interface friction, which is from the NCHRP 151 integrated cracking model, has to do with base friction. It is suggested that these values be used as the default values. In other words, the default values be used in design. The user does have an option to change each of these and can include their own specific values. Some of these values can be defined from calibration. For now, the default values shown on the screen were derived or determined, confirmed from the updated global calibration of the rigid pavement transfer functions that were completed in 2022. So it is suggested that these values be used by the designer unless they have revised these through their local calibration process. The next is the PCC joint spacing. The user can use a random joint spacing. A random joint spacing is typically not used any longer by industry, so a constant joint spacing is typically entered. This joint spacing also can vary. Typically, 15-foot joint spacing. In some cases, 20-foot joint spacings can be used or have been used. The next is the permanent curl warp effective temperature difference. We'll discuss this in more detail later in the presentation. The sealant type, on whether it's a performed or some other type of sealant, which includes non-sealant, liquid, and or silicone. Next option or design feature is whether there are tied shoulders or the user designer is planning to use tied shoulders, and the low transfer efficiency of those tied shoulders. 50% is the default values. That is the values that is suggested for use unless it has been determined by the user as a different value. Widened slabs is the next design feature. Is a slab widened? User can select widened slabs going from 13, 14. We'll also discuss this a little bit more in detail later in the presentation. So these are all of the design features for the jointed plane concrete pavement. While we're in the software, however, we thought we would very briefly go over the different layers included in a jointed plane concrete pavement. Almost any layer in a pavement ME layer library can be used for a jointed plane concrete pavement. Obviously, the first layer is the concrete slab for a jointed plane concrete pavement. Under that, we can have almost any material. We could have a default dense graded asphalt concrete layer for a flexible. We could also have under that or directly under the concrete pavement, we could have any type of unbound aggregate base layer, and also millings or pulverized cold recycled asphalt under the concrete. We can even have a permeable aggregate layer for drainage purposes that gets simulated in the Pavement ME software. I'm going to go ahead and remove these. Next, for the base, then we can, the subgrade or the chemically stabilized layer, we can have different types of chemically stabilized layers beneath the concrete slab. We can have a semi or cement stabilized layer under the slab. We can also have a soil cement under the slab. Any of these layers directly under the slab itself. And then past that, we can, any subgrade type is also allowed. different types of subgrade soils can be used, and different soil strategies can be included in the design. So this basically our design features, our design properties, and then the pavement structure. So I'm going to go back to the software or to the presentation and then continue. So we're going to start with the doweled joints first. We just discussed these specifically. So the dowel diameter can be included. Dowel diameter is typically a function of the concrete slab thickness. There are suggestions and recommendations provided in the MEPDG Manual of Practice on selecting an appropriate dowel diameter for the concrete slab thickness. Remember from an earlier module of this, Module 5, it was Module 5.1.1 on and 5.1.2 on cracking and faulting. The software does calculate the bearing stresses between the concrete slab and dowel itself, and that then defines whether we have an appropriate size dowel for the traffic and concrete slab thickness included in our design. So the dowel spacing typically is 12 inches on whether the dowel is, whether the transverse joint is doweled or undoweled. The next item is the erodibility index. As noted previously, we can have 5 different categories. This has to do with the material directly supporting or layer directly supporting the concrete slab. Recommendations in the MEPDG Manual of Practice are provided in terms of the erodibility index with the different types of layers supporting the concrete slab. So the MEPDG Manual of Practice provides suggestions for selecting an erodibility index depending on what type of layer you have supporting the concrete slab. Next, and this just shows the controls, allows you to select the resistance of the base course to erosion using an index on a scale of 1 to 5. And then the material erosion resistance determined both by its strength and durability. The Pavement software allows you to select one of the following options shown, and that's determined from the MEPDG Manual of Practice. Next is the PCC base contact friction. As we previously discussed, there's 2 categories: months until friction loss and whether we have an unbonded Jpcp or a fully bonded Jpcp through some time period, which is months until friction loss. The PCC base contact friction is the interface between the underlying base and PCC slab, which is modeled with or without full friction. The software allows you to determine whether or not the PCC base slab and base interface has full friction at construction, and how long full friction will be available at the interface if it's present after construction. This control also displays options available for modeling the PCC slab base interface friction. Next is PCC joint spacing. This is the PCC random joint spacing, which is typically the default values. However, the MEPDG manual of practice and even in industry to date, random joint spacings are not really built any longer, so a constant joint spacing is generally recommended. Next item is the permanent curl warp effective temperature difference. This input describes the combined effect of the PCC built-in temperature gradient at the time of concrete set, the effective gradient of moisture warping in the PCC going from dry on the top to wet on the bottom of the slab, the long-term creep of the PCC slab, and the settlement of the PCC into the base. It is defined in terms of the equivalent temperature difference. The software presents or includes a default value of a minus 10 degrees Fahrenheit, which was established as the optimum to minimize the error between the measured and predicted cracking and measured and predicted faulting during the global calibration. However, the user can select a different temperature difference value, -5, -15 or so, especially if a different value was defined during local calibration to minimize the error and any bias between the predicted and measured values. So, although in most cases the default value will be used as a minus 10 degrees Fahrenheit, the user does have the option to change that value. Next is going to be the sealant type. This control variable this variable allows you to select a sealant type applied at the transverse joint. There's two options, as we mentioned previously, preformed or other types of joint sealant. The other note to make is the sealant type is an input to the Jpcp transverse joint spalling model. Spalling is a key input for the Jpcp smoothness prediction that we just discussed in module 5.4.3 on smoothness or smoothness degradation. Tied shoulders is the next design feature. This input allows the user to, as a control, that you can select whether or not to use tied PCC shoulders. The PMED software allows you to select true, meaning you're going to have tied shoulders, or false, meaning there are no tied shoulder presence. In other words, no tie bars connecting the PCC slab to the shoulders, or we have different types of shoulders, asphalt concrete or gravel shoulders or no shoulders. The low transfer efficiency, this option allows you to define the long-term or terminal deflection low transfer efficiency at the lane or PCC shoulder longitudinal joint. The software provides a default value of 50%. That is the default value. Typical long-term low transfer efficiencies are somewhere between 50% to 70% for some of the monolithically constructed tied PCC shoulders, and 30 to 50% for separately constructed tied PCC shoulders. So the default again is 50%. The user does have the option to change that though. Next design feature is widened slabs. The widened slab, this control displays if the PCC slabs are widened. In other words, there's thickness, or the edge of the PCC slab extends beyond the edge stripe, if there is an edge stripe. The default value included in the software for the PCC slab is 12 feet. If there is a widened slab, this feature allows you to select whether or not the slab is widened and the width that it is widened to. True means that the PCC slabs are widened, and if they are, then the slab width is entered in this, either beyond 12 feet, 12 and a half, 13, up to 14 feet. False means selecting this option implies the PCC slabs are not widened, and the default value is 12 feet. However, the user, even if you do not have a widened slab, the user can select a narrower slab, such as 11 feet or so, if there is some special case where we have a narrower slab width than the default value. So now we'll turn to types of layers permissible in a jointed plane concrete pavement design strategy. What type of layers are permissible? We mentioned this or briefly overviewed this when the software was opened. So this is just going to be a review. So starting with the flexible layers, we can have default asphalt concrete. Below the Portland cement concrete slab, this can be, or typically is, a dense graded material. However, we can also have a permeable asphalt treated base layer beneath the concrete slab. The gradation and other volumetric properties of the permeable asphalt treated layer would have to be entered by the user. The only asphalt layer in the library presently is a dense graded asphalt concrete. But the user, and there in many cases a permeable asphalt treated base layer, is included beneath a concrete pavement. And that is applicable, but the user has to enter the specific layer properties for a permeable asphalt treated base layer. Chemically stabilized layers. We can have different types of chemically stabilized layer beneath a Portland cement concrete layer, and there can be more than one chemically stabilized layer. We can have a cement stabilized. We can also have soil cement, or even a lime stabilized soil if we have a very expansive soil. So different types of chemically stabilized layers can be entered beneath the slab. These layers can also be entered even if we have a dense graded or a permeable asphalt treated layer directly beneath the concrete slab. A chemically stabilized layer can still be entered beneath the dense graded or permeable asphalt treated base layer. Now, different types of non-stabilized or unbound aggregate base materials can be used. And these can vary from a dense graded aggregate base all the way to an open graded aggregate base, typically used for drainage purposes. In addition, millings and or pulverized asphalt, as well as pulverized concrete, can also be used as a base layer beneath the concrete slab. These types of base materials are simulated as an unbound aggregate base layer. The user needs to use judgment in deciding whether the material will behave as an unbound or bound layer, especially if millings or pulverized asphalt or pulverized concrete are being used, kind of as shown in this slide. So the millings can be used, pulverized or wrap can be used. With the design material properties, pulverized concrete can also be used, but there is not a layer in the library or the current software library for pulverized concrete. And then these other types of permeable aggregate, river run gravel, and or crushed gravel. So all of these can be used. This section of the module is simply going to include examples, selected examples, illustrating the impact of selected Jpcp design features on mid-slab cracking and transverse joint faulting. And most of these are going to be design features that the user has control over. However, we will also include examples that are typically not controllable by the user and or designer. So the first, mid-slab cracks or percent crack slabs is very sensitive to the PCC slab thickness because it reduces the tensile strains at the top and bottom of the concrete slab. And that's shown by the graph on the left, percent cracks slabs versus pavement age. With the blue, that's a Jpcp slab thickness of 8 inches. The green is 9 inches. The purple is like 10 inches, and then also there's 11 and 12 inches. So PCC slab thickness is extremely important to fatigue cracking of concrete pavements. Mean faulting as a function of pavement age. The concrete slab thickness or faulting is less sensitive to the concrete slab thickness. There are other design features we will show, like the use of dowels, that have a much greater impact on faulting and should be used to reduce faulting rather than trying to reduce faulting by increasing slab thickness. So this shows something very similar. Here's a concrete slab thickness of 8 inches, 9 inches, all the way up to 12 inches in terms of predicted faulting. So in some cases, faulting will increase if everything else is constant because the dowel diameter is relatively small for the PCC slab thickness, and so in some cases the bearing stresses between the dowel and concrete means we have an inappropriate size dowel, and when that condition occurs, faulting will increase. Next is going to be on the PCC modulus of rupture. The PCC flexural strength or modulus of rupture has a significant impact on the percent crack slabs, which is illustrated on this slide. The graph displayed on this slide shows the impact at different modulus of rupture values. The red line shows a modulus of rupture of 550 psi. The green is for 600, a modulus of rupture of 600 psi. The darker red one is 650, and the other two, the dashed, is 700 psi, and the blue one is 750 psi modulus of rupture. So you can see that the modulus of rupture can have a significant impact on the predicted percent crack slab. However, there is a relationship between the PCC strength and elastic modulus. We know that as the flexural strength or modulus of rupture increases, that the elastic modulus is also typically going to increase. So there's a relationship between PCC strength and elastic modulus. Increasing the strength typically results in an increase in elastic modulus. The graph displayed on the upper left hand of the slide shows a regression relationship between the PCC strength, the 28-day flexural strength, and the 28-day elastic modulus that is included in the software. The relationship or regression equation was included in Module 4.4.4 on the PCC material properties and will also be discussed in the next section of this module in greater detail. The percent cracked slabs increase with the lower flexural strength and lower elastic modulus. As strength decreases, the elastic modulus decreases in accordance with the Pavement ME software, and that results in an increase in the percent cracked slabs. When this relationship is in accordance with the regression equation included in the software. And like I said, we'll get into more detail on this in the next section of this module. Increasing the PCC width or using a widened slab reduces the tensile stresses and corner deflections of the concrete slab. So this shows the percent cracked slabs as a function of pavement age for different widened slabs. The blue is 12 feet. In other words, there is no widened slab. The green and the red that's not shown shows a 13 and 14 foot widened slab. And as you can see, that does have a pretty significant impact on percent cracked slabs. In addition, it also has an impact on mean joint faulting with age. The blue is no widened slab. The slab width is 12 feet. And then the red and the green are shown here with 13 and 14 foot widened slab. So a widened slab will reduce the mean joint faulting predicted by the Pavement ME software. A cautionary note regarding slab width. Using widened slabs increases the probability of longitudinal cracking in the slab. The software was not individually calibrated to longitudinal cracks simply because of using widened slabs. It is recommended that the designer resist the use of widened slab to not more than 14 feet or limit the width of widened slabs to 14 feet. Some industry, in fact, have recommended that 13 feet be the maximum width of the widened concrete slab. So just as a cautionary note, the longitudinal cracking of widened slabs was not specifically calibrated during the global calibration process. Joint spacing. Reducing the joint spacing reduces the curling and warping of the PCC slab and thus reduces the percent cracked slabs. In other words, this shows percent cracked slabs as a function of age throughout the design life, and this is joint spacing. This top dash curve, kind of orange, is a joint spacing of 18 feet. The next line is 17 feet joint spacing, then 16 feet, 15 feet, 14 feet, and finally joint spacing of 13 feet. So percent crack slab is significantly affected by joint spacing because of the curling and warping of the slab. More curling and warping for the longer joint spacing. The graph on the right shows the mean joint faulting as a function of pavement age throughout the design life. And as you can see, joint spacing has only a minor impact on mean joint spacing. So the designer should not start decreasing joint spacing to try to significantly reduce mean joint faulting. There's only a minor impact. In other words, shortening the joint spacing has a minor impact on reducing faulting of transverse joint, but a very significant impact on reducing percent crack slabs of jointed plain concrete pavements. The coefficient of thermal expansion. Typically, the designer normally does not, that this input variable, coefficient of thermal expansion, is not controllable by the designer, especially in areas where limited types of aggregates are available locally. However, lower CTE values reduces the curling and warping of the concrete slab, thus resulting in lower thermal movements. Selecting aggregates with lower CTE values, even if they have to be imported, can result in more cost-effective designs. As shown here, percent crack slabs, or the graph on the left, percent crack slabs as a function of pavement age through the design life. This dashed line is CTE value of 6. This one's 5.5, 5. Then we go down to 4.7, 4.5, and finally 4. And as you can see, there's a significant reduction in percent crack slab with the lower the CTE value, simply because it reduces the curling and warping of the concrete slab. Mean joint faulting as a function of pavement age throughout the design life, showing the same range of CTE values, and as shown, there is an effect, but the effect is much smaller for reducing mean joint faulting throughout the pavement design life by using different types of aggregates. So it would be potentially be cost effective to import aggregates with lower CTE values to reduce percent crack slab. It would probably not be cost effective to bring in aggregates simply to reduce mean joint faulting. Base layer, or the different types of base layers. The selected base layer types that are resistant to erosion and reduce erodibility, or the erodibility index, can reduce joint faulting of transverse joints. Selecting base layer types with higher resilient dynamic modulus values, or resilient or dynamic modulus values, like for asphalt base mixtures, will reduce the tensile stresses at the top and bottom of the concrete slab, and thus reduce percent crack slab. So, shown on the graph on the left, mean joint faulting as a function of pavement age throughout the design life. The blue is the aggregate base, which is the baseline. The green is an asphalt-treated base layer, and the red is a cement-treated base layer with a relatively high resilient modulus. And as you can see, the joint faulting is reduced by the type of base material, simply because we have the erodibility index is different, as well as the stiffness of those base layers are different. Percent cracked slab, shown on the graph on the right, versus pavement life throughout the design life, shows a difference in cracking. There is a difference. The difference is not as great as some of the other design features, but the blue represents the aggregate base. The dashed red is the cement treated base. The next line here, the solid red, is a cement treated base, but much stiffer stiffness than the cement treated. This is more like clean concrete. And then the ATB is shown here, percent cracked slabs, which is significantly less. So the primary reason percent cracked slab has to do with the erodibility index between these different types of base materials, as well as the modulus of the different base materials. The use of dowels, showing here the dowel diameter, will reduce the differential deflections across the transverse joint and significantly reduce the faulting of transverse joints. Remember from module 4.4.2 on faulting, the use of dowels significantly reduces the differential deflections across the transverse joints. And if we use an appropriate size dowel in terms of dowel diameter, it significantly reduces the bearing stress between the dowel as well as the concrete itself. Increasing the dowel diameter, as noted, will reduce the bearing stress and differential deflections, reducing the faulting at the transverse joint. So mean joint faulting is a function of pavement age throughout the design life. This purple dashed line, not using any dowels, so it's an undoweled transverse joint. The green has a 1-inch dowel diameter. The dashed line has a 1.2-inch dowel diameter, and finally this blue solid line, a dowel diameter of 1.5. So dowel diameter has a very significant impact, or can have very significant impact, on reducing faulting. Now let's move to the next section, in which we will discuss some of the important assumptions and things to remember when designing jointed plain concrete pavements. Two important variables that have a significant impact on the concrete layer thickness is the relationship between strength, flexural and or compressive strength, and the elastic modulus. This graph displayed in this slide illustrates that there are relationships between strength, in this case 28-day compressive strength, and elastic modulus, for which the same percentage of cracked slabs will be predicted throughout the life of the jointed plain concrete pavement. The solid line shown here shows the relationship of the 28-day compressive strength versus the elastic modulus. So at the end of 20 years, we have 15% cracked slab criteria. The dashed line, and this is for a 10-inch concrete slab. The dashed line is for a 9-inch concrete slab. And again, with the 28-day compressive strength versus 28-day elastic modulus, these combined values will result in 15% cracked slabs at the end of the design period. In other words, the only thing that we're changing within each of these relationships is the 28-day compressive strength versus 28-day elastic modulus to result in 15% crack slabs at the end of the 20-year design period. The short dashed line is for an 8-inch thick jointed plane, a slab thickness of a jointed plane concrete pavement. And again, this shows the relationship between the 28-day compressive strength versus the 28-day elastic modulus. So at the end of the design period, we result in, or the software will calculate 15% crack slab. So just simply as the 28-day compressive strength increases, there's an potential increase in the 28-day elastic modulus, so that the design criteria of percent crack slabs is 15% at the end of the design life. Now remember, the software uses the flexural strength in calculating fatigue damage, but as a user, you can enter the compressive strength. The software converts the compressive strength to a flexural strength. The relationship included in the software between 28-day compressive strength and 28-day flexural strength, or compressive strength converted to flexural strength, was presented in Module 4.4.4 on the concrete material property inputs. This slide illustrates that the measured laboratory strength versus elastic modulus can deviate from the standard relationship or regression equation between strength and elastic modulus embedded in the software, which was presented in Module 4.4.4 on PCC material properties inputs. Not to confuse you, but the strength variable included in this slide is the 28-day flexural strength, not the compressive strength. The 28-day compressive strength was included as a strength value in the previous slide for illustration purposes. As mentioned in the previous slide, the software converts the 28-day compressive strength to a 28-day flexural strength, or whatever age interval is included, using the relationship that was presented in Module 4.4.4 on the PCC material property inputs. It is important to understand the difference between the laboratory results and the regression equation for use in design, which will be illustrated or demonstrated in the next slide. In other words, this is the regression equation included in the PMID software, the solid black line, that if the user enters a 28-day flexural strength, then the PMID software will calculate the 28-day elastic modulus. However, the actual data that a user may enter could be different. In other words, there could be a bias. The circles shown on the graph here simply display from an individual state agency laboratory measured values of 28-day flexural strength versus 28-day measured elastic modulus, not calculated by the software. So the dashed line is simply the best fit line for the laboratory measured flexural strength versus elastic modulus in comparison to the solid black line, which is the regression equation included in the PMID software. This graph is complicated or shows a lot of information, but compares the data or observations included in the previous slides. In summary, the solid black line represents a 9-inch jointed plain concrete pavement thickness for which 15% crack slabs were predicted at the end of the design life, which is 20 years. The relationship between strength and modulus are compared that from the regression equation are then compared to the laboratory measured data, in other words, the blue circles, and the regression equation between strength and elastic modulus included in the software. So the laboratory data measure the flexural strength versus elastic modulus measured in the laboratory is now compared to the dashed line of the regression equation between flexural strength and elastic modulus that is included in the software, showing that there is a bias. And that's basically from the previous slide shown here. So it's important to recognize the regression equation shown by the dashed line in the PMed software exhibits the relationship displayed in the graph by the longer dashed line for calculating elastic modulus from the flexural strength in comparison to the laboratory measured data. In addition, it's also important to recognize that the software can be used to calculate the percent crack slabs as shown by the solid black line, for which 15% cracking would be calculated at the end of the design period, or of 20 years. So the solid black line illustrates the relationship between strength and elastic modulus, for which 15% crack slabs will be calculated by the software at the end of 20 years. So there's a significant difference basically between all three conditions. As such, the flexural strength elastic modulus values that plot above the solid black line for 15% crack slabs, designating 15% crack slabs, will exhibit more percent crack slabs or less resistance to fatigue cracking, simply because the elastic modulus is greater than for 15%, the relationship between, for 15% crack slab between strength and modulus. So for example, at a modulus of rupture of about, let's say, 675, to get 15% crack slabs, the elastic modulus would need to be about 3.5 million psi. Any values computed by the regression equation in the software or measured in the laboratory that have higher elastic modulus are going to exhibit through the software more cracking, because the tensile stress at the top of the bottom will be higher because the elastic modulus is higher for the same modulus of rupture. So all of this data will exhibit percent crack slabs above 15% crack slab criteria shown by the solid black line. Conversely, the flexural strength elastic modulus values that are below the solid black line, designating 15% cracked slab, will exhibit fewer percent cracked slabs or are more resistant to fatigue cracking. In other words, if we have, for the percent cracked slabs, if we have a modulus of rupture of, say, 775 psi, that results in a modulus of about 5.25 million psi. That will result in about 15% cracked slab. So any elastic modulus less than 5.25 million psi, either through the regression equation in the PMED software or through our laboratory data, will result in less than 15% cracked slab because the elastic modulus is less, and as such, the tensile stress calculated at the top and bottom of the slab will be less, and so the allowable number of load applications will be more, resulting in less fatigue cracking. In summary, the important point to recognize through this graph and illustration is the inputs to be used in design should follow the input levels used for calibration. In other words, if the laboratory measured values were used either for input levels 1, 2, or 3, those laboratory measured values should also be used in design. In other words, remember inputs level 1, 2, or 3 have to do with time-dependent flexural strengths entered by the user. Input level 2, time-dependent compressive strengths entered by the user, or input level 3, a 28-day flexural and or compressive strength entered by users, strength and modulus entered by the user. Conversely, if the concrete strength and elastic modulus relationship embedded in the PMED software was used for calibration, in other words, the PMED relationship or regression equation between strength and modulus was used for calibration, then that relationship should be used for design. The laboratory measured values above, just remember the laboratory measured values above the solid line of the regression equation included in the PMED software mean the strength, elastic modulus, concrete strength values are less resistant to fatigue life in comparison to the PMED equation, while the laboratory measured values below the solid line represent concrete mixtures that are more resistant to fatigue cracking. For some PCC mixtures, the strength elastic modulus may have the same slope but be above or below the regression equation included in the PMED software. The data set to be used in design should follow the data set used for calibration, as noted on the previous slide. So what's shown on this slide is simply another example of the 28-day modulus of rupture versus the 28-day elastic modulus. The circled orange data represent data from one agency. The solid black line represents the relationship between the PMED included in the PMED software itself. And there can be a bias between the input levels for PCC strengths. So, in other words, if the laboratory, to reinforce the statement previously made, if the laboratory measured values were used either for input levels 1, 2, or 3, those laboratory measured values should be used in design for different types of concrete mixtures that the agency typically uses. If the concrete strength elastic modulus relationship embedded in the software was used for calibration, in other words, the user is entering the modulus of rupture and having the software calculate the elastic modulus, then that relationship should be used for design. In other words, input compatibility. So as such, input compatibility is important. It is important to know and follow the process and variables used for the calibration process, not only for concrete, but for other materials. As stated for the previous slide, if the concrete's strength elastic modulus regression equation, in other words, the solid black line, was used for calibration, then it should be used for design. However, if laboratory measured data were used for both strength and elastic modulus, in other words, strength and elastic modulus value were measured for calibration, then those laboratory measured strength and elastic modulus values should be used for design. Remember from Module 4.4.1 on subgrade soils and Module 4.4.2 on aggregate base materials, the resilient modulus of any unbound layer should be compatible with the water content and dry density entered for a specific design. As mentioned in the MEPDG Manual of Practice, under Chapters 3.5, Factors and Features, excluded from the MEPDG, durability and disintegration, material disintegration of the PCC slab, as an example, decracking, is not predicted by the software. It is assumed that the PCC materials and mixtures will be designed to prevent any durability issue from occurring throughout the design life. Spalling along the transverse joints is predicted by the software. But in those predictions, it is assumed that the PCC mixtures are being designed, produced, and placed to meet standard minimum material specification requirements of the agency, such that decracking and other such types of material-related distresses do not occur or will be minimized. As mentioned in the MEPDG Manual of Practice under Chapters 3.5, Factors and Features excluded from the MEPDG, volume change of the soils in terms of frost heave and or frost susceptible soils and or potential vertical rise from expansive soils is not predicted by the software. It is assumed that the subgrade will be properly treated and constructed so significant volume change of the soils is minimized and does not become an issue throughout the design life of the Jpcp. Another assumption or things to remember. Remember, the distress threshold values and or design criteria need to represent the agency's policy of when to rehabilitate or repair the pavement. So these values represent the condition of the surface that triggers some type of major rehabilitation. Another thing to remember, the functional performance of the pavement is estimated through the calculation of IRI throughout the design life. IRI is heavily dependent on pavement distress, as well as the site factor for some climates and soil combinations. Removing and replacing problem soils, for example, highly frost-susceptible soils or highly expansive soils, can reduce the impact of the site factor on the increase in IRI over time. This next section of this module will focus on interpreting and adjusting a jointed plain concrete design to satisfy the design criteria and reliability level selected by the user. When a trial design does not meet the design criteria or reliability level, what needs to be adjusted or changed to achieve an acceptable design? In other words, what variables should we as a designer look at for changing so that we do achieve an acceptable design? This section provides some suggestions on determining what input and design strategy variable or design feature should be changed in adjusting the designs to satisfy the design criteria and reliability level selected by the user. Some suggested steps to take in adjusting a Jpcp design to achieve an acceptable design are noted on this slide. Kind of the first is to determine the distress criteria or performance measure that did not pass. So which one is controlling our design and needs to be reduced? The second is to check the site factors to make sure they are reasonable for design. The third is to check the inputs. Are they correct? In other words, have we made a blunder in entering the input, the values for the inputs? So checking the site factors and checking the inputs are steps that should be taken to ensure that they are correct and reasonably represent our pavement structure. The fourth is to identify one or more design features that have a significant impact on the values that did not pass. This relates to the information that was included in the MEPDG Manual of Practice in Section 13.5 or Table 13.5. That is the focus of this section. And the fifth is to change one design feature at a time to understand its impact on the trial or our preliminary design strategy. It's generally not suggested to change multiple, 2 or more design features at the same time to achieve an acceptable design unless you're using the optimization feature of the Pavement ME software. So it's generally suggested change one feature at a time so that you understand or know its impact on the distress, criterion, or performance measured that did not pass. Table 13-4 in Chapter 13 in the MEPDG Manual of Practice provides suggested modification for reducing the distresses to achieve an acceptable design. The user or designer should focus on the input parameters controllable by the designer that have a significant impact on those predicted distresses and or performance measured. So these tables that are going to follow simply identify the design factor or feature that have a significant impact on the design criteria or variable, mid-slab cracking, faulting, and IRI. The number of check marks within each category designates its importance or sensitivity to the design variable. So 3 check marks means it's very important. 2 check marks means moderately important. 1 check mark means it has an impact, and if it's not listed, it's generally no impact on the calculated design variable or distress. So this table displayed in this slide simply illustrates the importance of the design factor or feature in changing the distress variable. So increasing the slab thickness significantly reduces mid-slab cracking and only slightly reduces faulting. It has really no impact on IRI when you exclude its impact already for mid-slab cracking and faulting. So obviously slab thickness does have an impact on IRI, but its majority of its importance is defined through the impact on mid-slab cracking, through the impact on faulting. So just for IRI, it has a very minimal to or a nil impact on IRI. Increasing the modulus of rupture significantly reduces mid-slab cracking, but has no impact on faulting and IRI. IRI is definitely impacted by the modulus of rupture, but only through the impact of reducing mid-slab cracking. Shortening or reducing joint spacing significantly reduces mid-slab cracking and slightly reduces joint faulting. A lower CTE value will significantly reduce mid-slab cracking and also have a moderate impact on reducing faulting. The use of widened slab significantly reduces mid-slab cracking and has a moderate reduction on faulting and a low impact on reducing IRI. Continuing with the impact of different design factors or features on the different distresses. The use of dowels and the use of larger diameter or appropriately sized dowels significantly reduces faulting and has a much less impact on reducing mid-slab cracking. The use of erosion-resistant base layers and or base layers with a higher elastic or resilient modulus will moderately reduce faulting and IRI, but has a minor impact on mid-slab cracking. The use of tied PCC shoulders has a minor impact on reducing mid-slab cracking and faulting. The option of reducing and replacing problem soils with selected impact materials can have a moderate to significant impact on reducing IRI, but only a minor to low impact on reducing mid-slab cracking and faulting. Reducing or requiring a lower or smoother Jpcp at the time of construction can have a significant impact on IRI depending on the additional smoothness requirement, but basically has no impact on mid-slab cracking and faulting. There are other input variables that have a significant impact on the Jpcp distresses, but the designer generally does not directly control the inputs for these design features or input variables. The first, the permanent curl warp effective temperature difference, has a significant impact on mid-slab cracking, as well as a moderate impact on faulting. The lower the temperature difference, the lower the mid-slab cracking and faulting. However, the designer generally does not control this value, with the exception of some design build projects. In addition, sometimes nighttime versus daytime construction practices can also reduce the permanent curl warp effective temperature difference. This was discussed earlier within this module, as well as within the module 4.4.1 or 4 on the material property inputs for concrete pavements. So this is an important variable, but it's usually not controllable by the designer. It's usually defined through the global and or local calibration process, or can be defined through the calibration process. Again, certain construction techniques can have an impact on this variable, and if that can be definable, then the designer would be encouraged to use those values. Traffic volume is not controllable by the designer unless the designer is adding more lanes to the project. However, traffic volume has a significant impact on mid-slab cracking, as well as a moderate to significant impact on faulting. Climate and or location has an impact on cracking, mid-slab cracking, and faulting, but a much larger impact on IRI because of the site variables related to climate. Subgrade type also has a minor impact on mid-slab cracking and faulting, but a larger impact on IRI because of the site factor variables related to soil type. The combined impact of climate and subgrade soil itself can have a very significant effect or impact on IRI versus them individually. So the combined impact potentially has a significantly impact on IRI. The designer should not blindly select any Jpcp design feature or input variable to try to reduce one of the distresses that did not meet the design criterion. Some adjustments that are usually not cost effective in reducing the distresses are listed on this slide. For example, increasing the PCC thickness to reduce faulting or IRI is generally not cost effective. Increasing slab width just to reduce IRI is usually not cost effective. Reducing the transverse joint spacing to reduce faulting or IRI is usually not cost effective. Increasing the PCC strength and or reducing the elastic modulus of the PCC slab to reduce faulting and or IRI is usually not cost effective. In summary, there are other design features and factors that were noted in the previous tables that are not cost effective for reducing certain distresses. Or let me state that differently. There are other design features and factors that are not cost effective for reducing certain distresses of jointed plain concrete pavements that were noted in the previous tables. In other words, their sensitivity or the distress sensitivity to those values are low. Thus, the designer should select only those variables that have a significant impact on reducing the distress, not meeting some criterion established by the designer for the specific design. Next is a summary of the Jpcp design module itself. In summary, the summary or learning outcomes from this module on Jpcp designs were: first, we defined and located the Jpcp design features used in the PMID software. We identified the types of pavement materials permissible in a Jpcp design strategy. We illustrated the impact of selected design features and input variables on the predicted Jpcp distresses. We explained and identified some of the assumptions used in the Jpcp design strategy. And finally, we listed the Jpcp design features to adjust or change the design to achieve an acceptable design strategy and are the ones that would be more cost effective. In addition to the outcomes from this specific module, 5.1.4, remember from the previous 3 submodules under 5.1 on Jpcp distresses. Module 5.1 provided the following outcomes, or the following overall outcomes. We first described the Jpcp transfer functions for mid-slab cracking. We also described the Jpcp transfer function for faulting. And then the third and finally, we described the Jpcp regression equation for smoothness degradation, or IRI. This concludes Module 5.1 on jointed plain concrete pavement design strategies and transfer functions, and interpreting and revising design strategies for jointed plain concrete pavements. The next module of the training course, sequencing, is Module 5.2 on CRCP design strategies and transfer functions.